Guy ILS Montessori and School. Grade 9, Physics. Federal Board Islamabad. 2025 onwards syllabus. Summary of Chapter 4. Kinematics from Cantab Publisher Book, Federal Board Islamabad. Chapter 2. Kinematics from NBF Book, Federal Board Islamabad. Summary of Chapter, Kinematics. Introduction to motion. In the world around us, everything is either moving or staying still. For example, a book on a table is at rest relative to the table, while a person walking in a room is in motion as their position changes relative to the walls. Motion is not just about movement but also about how objects move, whether in straight lines, curved paths, or around fixed points. Types of motion. 1. Translatory motion. Each part of the object moves the same distance, in the same direction, and in the same time. Example, a ball moving in a straight line, linear motion, or a car moving on a curved road, curvilinear motion. 2. Linear motion, rectilinear motion. Objects move along a straight path. Example, a falling apple or a ball rolling straight. Curvilinear motion. Objects move along a curved path. Example, a car turning on a road or an electron revolving around a nucleus. Rotational motion. Objects spin around a fixed point, pivot. Example, a spinning top or a ceiling fan. Random motion. Objects move irregularly without a definite path or direction. Example, a butterfly flitting or dust particles in a light beam. Vibratory motion, oscillatory motion. Repetitive back and forth movement around a central position. Example, a pendulum, a plucked guitar string, or a child on a swing. Concepts of distance, displacement, speed, and velocity. Position. Describes where an object is located relative to a reference point, origin. It is a vector quantity, including both distance and direction. Example, moving 5 meters to the right of the origin gives a position of plus 5 meters. Distance versus displacement. Distance. Total path covered by an object, regardless of direction, scalar quantity. Displacement. Shortest straight line distance between starting and ending points, with direction, vector quantity. Example, a person walks 5 kilometers to point B and 3 kilometers to point C. Total distance equals 8 kilometers. Displacement is calculated using Pythagoras theorem. Speed versus velocity. Speed. How fast or slow an object moves, without direction, scalar quantity. Velocity. How fast or slow an object moves, including direction, vector quantity. Example, a car moving east at 60 km per hour has a velocity of plus 60 km per hour. If it moves west at 60 km per hour, its velocity is minus 60 km per hour. Conclusion. Understanding motion involves analyzing how objects move, the paths they follow, and quantifying their movement using concepts like distance, displacement, speed, and velocity. These foundational ideas help us describe and predict the behavior of objects in our world. Calculating speed and understanding its types. Introduction to speed. Before Galileo, movement was described qualitatively as slow or fast. Galileo quantified motion by defining speed as the distance traveled divided by the time taken. Speed is a scalar quantity, derived from distance and time, and its SI unit is meters per second, meter per second. Other units include kilometers per hour, kilometer per hour, and miles per hour, mph. For example, if a cyclist covers 21 meters in 3 seconds, their speed is 7 meters per second. Speedometers measure speed without indicating direction. Here is its formula. Speed equals distance divided by time. Types of speed. 1. Instantaneous speed. This is the speed of an object at a specific moment. For example, a car traveling at 70 km per hour covers 70 km in 1 hour, 35 km in 30 minutes, and approximately 19.4 meters in 1 second. Instantaneous speed is calculated as the ratio of a very small distance to an extremely brief time interval. 2. Average speed. This represents the overall speed for an entire journey, calculated by dividing the total distance traveled by the total time taken. For instance, if a car travels 20 km in 30 minutes, 10 km in 10 minutes and 10 km in 20 minutes, the average speed is 40 km per hour. Average speed smooths out variations in speed during the trip. Here's the formula for average speed written explicitly. Average speed equals total distance divided by total time. Uniform and non-uniform velocity. Uniform velocity occurs when an object moves in a straight line at a constant speed without changing direction. Equal displacements occur in equal time intervals. This is also called uniform motion. Non-uniform velocity happens when an object's speed or direction changes over time. For example, a car on a curved track may have constant speed but changing direction, resulting in non-uniform velocity. Average and instantaneous velocity. 1. Average velocity. This summarizes an object's overall motion by dividing the total displacement by the total time. It does not account for variations in speed or direction during the journey. The SI unit is meters per second, meter per second. Average velocity equals displacement divided by total time, where displacement is change in position. Note, velocity is a vector quantity, so it includes direction, unlike speed, which is a scalar quantity. 2. Instantaneous velocity. This measures an object's velocity at a specific instant, calculated as the ratio of a very small displacement to an extremely brief time interval. For curved motion, like circular motion, instantaneous velocity aligns with the tangent at any point. For example, a stone revolving in a circle, if released, moves along the tangent. Acceleration and its types. Acceleration is the rate of change of velocity over time. It occurs when an object's speed or direction changes. A car speeding up, slowing down, or turning are all examples of acceleration. Formula of acceleration. Acceleration, equals change in velocity, delta v, divided by time interval, delta t. The SI unit of acceleration is m per square second, meters per second squared. Types of acceleration. 1. Average acceleration. Defined as total change in velocity divided by total time taken. Formula. Acceleration, equals velocity final minus velocity initial, divided by time. 2. Instantaneous acceleration. Acceleration measured at a specific instant. It is obtained when the time interval approaches zero but not exactly zero. Positive and negative acceleration. Positive acceleration. When velocity increases over time. Example, pressing the gas pedal. Negative acceleration, deceleration or retardation. When velocity decreases over time. Example, applying brakes. Uniform and non-uniform acceleration. 1. Uniform acceleration. Velocity changes by equal amounts in equal time intervals. Example, a freely falling object under gravity. 2. Non-uniform acceleration. Velocity changes by unequal amounts in equal time intervals. Example, a car moving in traffic or a roller coaster. Acceleration due to gravity, g. Objects in free fall experience a constant acceleration due to Earth's gravity. Acceleration due to gravity, g, approximately equals 9.8 meters per square second, or approximated as 10 meters per square second. It acts downward towards the center of the Earth. When moving upward, objects decelerate at negative g until stopping at the highest point. When moving downward, objects accelerate at plus g. Velocity in free fall. For an object in free fall starting from rest, velocity initial equals 0, velocity after time t is v equals g times t. Example calculation, if t equals 2 seconds, then v equals 10 times 2 equals 20 meters per second. Gravitational acceleration is independent of mass. In a vacuum, all objects fall at the same rate, regardless of mass. Example: a coin and a piece of paper fall together when air resistance is absent.
Grade 9 Physics. Graphical Analysis in Motion. Distance time graph and displacement time graph. In this graph, time is usually plotted on the horizontal axis, x-axis, and distance on the vertical axis, y-axis. To sketch and plot a distance time graph, follow these steps. Begin by drawing two perpendicular lines, one horizontal and one vertical, to represent the x-axis, time, and y-axis, distance, respectively. Mark the x-axis for time, typically in units like seconds, minutes, or hours, and the y-axis for distance, in units like meters or kilometers. Using your data set of time and corresponding distance, plot a dot for each pair of values on the graph. Each dot represents the distance traveled by the object at a particular time. Connect the dots in the order they were plotted. If the object is moving at a constant speed, the dots will form a straight line. A changing speed will result in a curved line. Slope of distance time graph. After understanding the plot of distance/displacement time graphs, we explore the concept of slope, which is helpful in understanding the nature of motion. The slope of a graph represents the rate of change of one variable with respect to the other. On a distance time graph, the slope indicates the rate of change of distance over time, which is the speed of the object. This is read as slope is equal to rise over run, which is equal to the change in distance divided by the change in time, equating to speed or velocity. Finding the slope at a specific point. Curved line. If you have a curved line on a graph, referenced in figure, and want to find the slope at a specific point, follow these steps. Draw a straight line, tangent, that just touches the curve at that specific point without cutting through it. Using this tangent, sketch a triangle with a right angle. Calculate the slope using the triangle's vertical and horizontal sides, just like with a straight line. Interpretation. Distance and displacement time graphs are important for understanding how graphs can reveal information about an object's motion. By examining the shape and slope of these graphs, we can determine not only the speed and velocity of an object but also understand its pattern of movement over time. Whether the object is accelerating, decelerating, or moving at a constant speed, these graphs provide a clear visual representation of its journey. Object at rest. If the distance time graph is a horizontal straight line, the slope of the graph has a zero value, indicating the zero speed/velocity of the object, i.e., the object is at rest. Object moving with uniform speed or velocity. If the distance time graph is a straight line, the slope will be constant, indicating the constant speed of the object, i.e., the distance it covers increases uniformly with time in a given direction. The displacement time graph for such motion is shown in the figure, which is inclined downward, representing the negative slope, negative velocity. A steeper straight line graph represents a larger slope, high speed, indicating that a large distance is covered in a short time interval. This is represented in figure, in which graph A represents a higher speed than graphs B and C. Knowledge 4.8. Determination of distance covered. To illustrate this concept, consider an object moving with uniform speed v in a straight line for a time interval t. The distance covered by the object can be determined using the equation s equals v times t equals vt. This is read as distance equals velocity multiplied by time, which equals vt. Representing the area under the speed-time graph, A rectangle with length t and width v shown in figure 4.36. This geometric interpretation confirms that the area numerically represents the distance covered.